Yeah, so my plan is to give a very, very simple introduction to what many people know as reconstruction program or problem, okay, depending on your taste, okay? So I want to explain what the problem is, and so hopefully, I will convince some of you at the end of the lecture that, this is an interesting problem, okay? So I should say immediately before I start with anything that this problem is widely open, okay? All right, okay, so let me start something very basic. So I will start with what people call the symmetric tensor category. Okay, and instead of giving the definition, I would just start with an example. So definition by example. Okay, so the example I have in mind, in fact, I can be more general, but let's take G be a finite group. Okay, and let me see. Okay. Sorry, I'm trying to adjust my screen here. So let G be a finite group. Let's take the set, the rep of G. Okay, this is the set of representations of G. And this set is interesting set. This set is endowed with two operations. So there's a direct sum. If you have two representations, say VI1, 2 reps of G, then you can take direct sum. Okay, this is also a rep, an element in rep G. There is also a tensor product. So you can take the tensor product. Let's take a finite dimensional representation, so we don't have to worry about topology here. So the tensor product is also a representation of G. Okay, so with this direct sum and tensor product, this rep G is a tensor category. Okay, and so I will usually focus on semi-simple case, okay, which means that my tensor category has only, in the case of finite group, obviously, the only finite number of irreducible objects. Okay, so that's the case I'll focus on. And what do I mean by symmetric tensor category? Well, symmetric tensor category is so symmetric means that let's just take a representation of V, and in this case we can take a flip. Okay, and this flip turns out to be an isomorphism between representations of G. Okay, so so that's what symmetric tensor category means. Okay, one could be more general, put different V1, V2, and then you keep track of the indices. I'm not going to do that. Okay, one thing I like to point out is that this symmetric tensor category has the property that if you apply twice, you will get identity. Okay, because this sigma 1, 2 simply switch tensors. Okay, so this is what I mean by a symmetric tensor category. Okay, and even though I didn't give the definition, because if you want to define category, you have to have various conditions, compatibility, coherence, and so forth. But I will not define that. But let me just state a theorem, which is actually so I'm not going to state it in a very precise way, but I would just give you some idea of what the theorem looks like to motivate what I would discuss next. Okay, so the theorem is that So this theorem is due to Deligne. Oh. May have misspelled Daligne's name, but so this comes from algebra geometry, and in the C-star category setting is due to Doppler-Roberts. Okay, which basically says the following. So if you have a symmetric tensor category, if C is a symmetric, let's say a tensor category. So by this, I mean, it's semi-simple, a finite number of objects, let's say, and it is symmetric in the sense that there's this flip, and the square of the flip is equal to identity. So if you have a tensor category like this, then you can always find, in fact, a unique group G such that the G is going to be a finite group in this case. If I define my tensor category to be semi-simple with only finite number of objects, the actual theorem is more general, so we do not require that it has finite number of objects. But let me just scratch that. Let's just consider the simple case. So that's why the theorem is in quotation marks. So I'm now stating the theorem in full generality, and in the way I'm presenting here is it's a small part of the general theorem. Okay, so there is a finite group such that the C is actually the same as the representation category of G. Okay, so this is so hopefully this theorem shows that why I just give you example without even writing down the axioms, right? Because this example turns out to be the only example, right? In some sense, and of course you see this theorem comes from two different areas and with complete different motivation. Okay, so I'm not too familiar. I know something about Daligne's motivation, but let me talk about Doppler-Roberts motivation. So Doppler-Roberts, they're concerned with a question which comes from algebraic quantum field theory. So their paper, the paper by Doppler-Roberts, I think I forgot the exact reference, but the paper has the following title. At least one of the papers has the following title. The title is "Why is there a compact group associated with every quantum field theory?" As again, this is not exact title, but but in a sense, that's what's in the title. One of the papers proving such a theorem. Okay, so basically, this compact group, what's called gauge group, comes out of some representation category, and in certain quantum field theory defined over in 4 dimensions, the space-time dimension we live in, Doppler-Roberts find a category structure, and that category structure indicates that it has to come from the representation of a compact group. Okay, so that's basically the motivation. Okay, so this is a prototype of a reconstruction. Okay, so what are we reconstructing here? So we're given some theory with some abstract structure, and we can abstract those structures and become some kind of category, in this case, a symmetric tensor category. And what is being reconstructed here is this compact group, okay? More precisely, what Doppler-Roberts did was that they have a universal quantum field theory. The compact group was constructed so that when you take the orbifold of that, free theory with respect to its orbifold, the representation theory of the resulting orbifold gives you the symmetric tensor category. Okay, so this quantum field theory is in dimension greater or equal to 3. Okay, so that's the high dimensional story. But in lower dimensions, the situation is very different, and in some sense is richer. Okay, so let me go on to the second part. Let's see, it's the second part, which is the reconstruction. problem. Okay. So so what replaced the symmetric tensor category in the case of reconstruction problem is the modular tensor category. So we're going to replace this symmetric tensor category with modular tensor category. Okay, so MTC for short. Okay, so this is a tensor category with very rich structure. So one distinguished feature of this modular tensor category is that we still have V, tensor V, and there is a morphism between these two. Let's write B12. Okay, but this B12 and a squared is no longer identity. Okay, it's not going to be just like a flip in the case of symmetric tensor category, and together with some axioms. For instance, the most important one is probably the non-degeneracy of this S matrix. Okay, so so there's some similarity, but it's very different from the symmetric tensor category. So I'm not sure if everybody knows the definition, but I will not actually go over the definition here. Okay, just maybe I'll have examples later on. Okay, if you guys have any questions, feel free to interrupt me. I feel like I'm talking to the screen. So anyway, yeah. So modular tensor category, in some sense, you know, is a richer. I mean, from a mathematical point of view, because this, you know, there's this interesting representation of Bray group here. Instead of the symmetric group, you have representation of Bray group, and has something to do with low dimensional topology. Okay. So that's one of the reasons people are really interested in this modular tensor category. I should say, I think probably this was first defined by Rashid and Turiev, and Turiev has a big book on modular tensor category. Okay, which I highly recommend it. So everything is pretty clear in that book. Anyway, so so now our object is, our category is going to be, you know, in some sense, a richer category because of its connections with, you know, Bray group, low dimension topology, TQFT, and so forth. Okay, so this is a very, very interesting category, and one of the source of such category, so is the following. So let me take a look at my time here. So this is a 1 hour talk, and I have already talked for like almost 20 minutes. So yeah, so I think I will, yeah, so let's see, how do we do this? So I have said that you replace symmetric tensor category with modular tensor category. So what to replace? This group G, okay? What kind of symmetries, you know, what kind of things that replace G in the case of symmetric tensor category? And this turns out to be a very interesting question, and the answer to this is not, you know, it's not easy to define the analog of this group G in general, okay, for modular tensor category. Okay, for some people it may be quantum group UQG, when Q is a root of unity. Okay, that's one source. And for me, I think what replaces G is this what we call a conformal net. Okay, in particular, conformal net, which is rational. So maybe I will write down a rational conformal net. Okay. Unfortunately, I don't think I have time to maybe define this precisely. So maybe instead of giving you the definition of conformal net, I would just give you example of a conformal net. Okay. So what is the example of a conformal net? Well, If you let's take a very simple example. So let's take example where let's consider what's called a loop group L. Let's say LSUN. Okay, so these are space of smooth loops with value in SUN, the Lie group, and this loop group has a very interesting class of representation called positive energy representation. And from this positive energy representation, you can produce a conformal net. Okay, and it turns out this for this conformal net, the reducible representation of the conformal net are in one-to-one correspondence with those positive energy representations at some fixed level K. Okay, so maybe I'll write ASUNK. Okay, so this is a rich source of conformal net, and the interest in such rational conformal net is because of the following result. I think this result is due to KLM, Kawajikanshu-Langdon-Mueller, which says that if A is rational, if A is rational, then the rep of A is a modular tensor category. Okay, more precisely, this is a unitary modular tensor category since I'm talking about conformal net here. Okay, so what replaced this group G in the previous section is really this rational conformal nets. If you're interested in unitary modular tensor category, then the representation of this conformal net is a unitary modular tensor category. Okay, so I think I don't know people's background in the audience. If maybe some people who are into vertex of the algebras. So in that setting, if you take A to be a rational VOA, then the representation of A is going to be a modular tensor category, not necessarily unitary. Okay. All right. So let me state the reconstruction problem. So the problem is very easy to state. So suppose given a modular tensor category, let's say C. So the version I'm going to state right now, let's state it for conformal nets. I can also state it for vertex operator algebra. So let's put a unitary modular tensor category C. Is there a conformal net, a rational conformal net, A, such that C is the same as rep A? Okay, so that's I guess the conformal net version. I can also state it in, for instance, in the VOA version. It's slightly more general. Given a modular tensor category C, is there a let's say a rational VOA? Maybe I write V such that C is isomorphic to rep of V. Okay, so depending on your background, you might prefer either one of these versions. Okay, the second version is slightly more general because you don't have to impose unitarity condition, but either way, this is a reconstruction problem. Okay, so you can see there's some similarities between this and the previous. In the previous case, it's really a theorem, right? There's always a G, so that rep G is the symmetric tensor category. But here, we don't know. We don't know the answer. So this problem is widely open, and so maybe I would take either version of this, and maybe I make one remark immediately. Okay, one remark is that this A, of course, this A of V is highly non-unique, right? Because if you take, for instance, if you take what's called holomorphic VOA or holomorphic conformal net, so for instance, such example is a V sharp, right? The one associated with moonshine, then the rep of V is trivial. So this is a modular tensor category with only one object. Okay, so and if you take any rep V tensor V sharp, that will be the same as the rep of V. Okay, so the underlying modular tensor category is highly non-unique, and you can also see that this so-called holomorphic conformal net or VOA. That's just a holomorphic. That's just a conformal net or VOA with trivial representation. So the only representation, reducible representation, is the vacuum representation. Okay, so you can see that perhaps in some sense these holomorphic things will play some role, and we'll see that later on. The holomorphic ones will be interesting. Okay, so I hope the problem itself is clear, and that's provided you guys know a little bit about the the rational VOA or the rational conformal net. So I didn't quite have time to discuss the definition of rational conformal net.
Question.
Yeah.
Question.
Yes, please.
And can I think this? Can I think this conformal net as like a Wilson loop?
No. Wilson loops, they're observables in a quantum field theory, right? The conformal net is underlying symmetry.
Okay.
Yeah. So this is like, yeah. So Wilson loop, they're like operators, and when you consider expectation values, this would be correlation functions. So what I have here is really the underlying symmetry of the system. And since we're talking about conformal field theory, so the underlying symmetry at least includes the diffeomorphism group or the Riverside algebra if you're doing this on the Lie algebra level. So this is like a symmetry algebra we're talking about.
Okay, thank you.
Sure. Yeah, so let's see. Yeah, so yeah, I'm sorry, I didn't. Well, I guess that's one advantage of having transparency. So if I have transparencies, I could have flashed a few pages of the definition of conformal net. They're in some sense, the symmetry, the underlying symmetries. So for instance, the example I give here, so I guess in the physics literature, this would be like the current algebra. Okay, and so in other words, underlying algebra in this particular example corresponds to current algebra, and we're studying the representation of this current algebra. It turns out in this case, the corresponding representation theory is well understood, is rational, so there are only finite number of irreducible representations corresponding to finite number of primary fields. So this is, I guess in the physical literature, is the WZW model, okay? All right, so yeah, so that's the problem. I think this is, is well defined, so it's certainly a well-defined problem. And so let me say a few words. I have remarked that it's not unique. Okay, so that might be, that might make somebody unhappy because, we're used to beautiful theorems where things exist and unique, but this one, just because of the nature of things, it's not unique. But nevertheless, I want to convince you in the maybe next half an hour or so that this is a really interesting question. And yeah, so let me see. I make the first remark, and the second remark is that there's no counterexample. Okay, by this I mean if you come up with unitary modular tensor category, is there rational? So can you show that there's no rational conformal net such that C is isomorphic to that? No counterexample in the following sense. Okay, so the most famous one, I guess, is the Hargrove subfactor. I'm sorry, I may have misspelled Hargrove. Sorry about that. Hargrove subfactor. So for those of you who know what this is the, the I guess one of the most or the most interesting exotic subfactor. And that subfactor does not give to modular tensor category immediately, but in subfactor theory, there is something called the double construction, and it can produce a modular tensor category out of the double of the corresponding fusion category. And so this gives rise to a modular tensor category, what we call the exotic, okay? And so there are a lot of work in recent years trying to show that, maybe there's some conformal field theory or behind this exotic modular tensor category. I think one such class of works, a series of papers written by, I think, Tara Gellman and his co-author. So they're getting pretty close to produce a candidate. Okay? They produce a candidate in the following sense: they're able to actually write down the characters of the corresponding chiral algebra. Okay, the way they do this is by computing the SD matrices, and they have a way of producing a character of the corresponding chiral algebra. And the amazing thing is that in that character expansion, all the coefficients are positive integers, which it should be the case if you have underlying chiral algebra. Okay, but as far as I know, nobody has succeeded in identifying the corresponding chiral algebra. Okay, so there's still questions open. I think most recently, if I remember correctly, there are also some people doing lattice, doing the integrable lattice models, and when you take the lattice size going to 0, you might produce a conformal field theory. So there are also some work in this direction, I think, even within the last year or so. But still, I don't think we're able to actually, say that, that's the conformal field theory, which gives rise to the double of Hager subvectors. So this is still open. So when I say no counterexample, I mean, there's no definite theorem which says that, this is a modular tensor category doesn't come from, conformal field theory because of this, right? So there are no such counterexample yet, okay? And let me see what else I want to say. Okay, so yeah, so that's the case, and so in some sense this is not easy problem. Okay, even in concrete examples to produce such a conformal net or such a VOA, it's not a not easy problem. So maybe I'll mention one thing, number 3. As you will see that I have more questions than theorems. So I think I should probably at least mention one theorem. Okay, so maybe I will mention one theorem. So one such theorem which is sort of motivated. So maybe I'll say a few words about how this theorem is motivated. Okay, so let's give given a modular tensor category C. Okay, so this is a modular tensor category. Okay. So suppose that we can find this conformal net A such that the rep of A is the same as this modular tensor category C. Okay. In the case of conformal net, or in the case of conformal field theory, there's a construction called the permutation obifold. Okay, so let me say a few words about this obifold. So what you do, maybe I would do just to, okay, so let's do N. Okay. So you take tensor product of this net N times, and then the symmetric group on N letters. Okay, so sigma X on this N tensor product by permuting the tensors. Okay. So, and this action turns out to be proper. So, and notice that if you take any group, any finite group, this group, of course, embed into Sn when n is sufficiently large, right? So, for instance, you can take n to be the cardinality of the group G. So, any group can act on this A tensor with itself n times when n is sufficiently large, and then you can take the obifold, right? So, take this n and then take the fixed point algebra. Okay, so this gives the orbifold construction. Okay, oftentimes people take example people would take would be Zn. Okay, so this is the cyclic group generated by this tensor 1, 2, 3 to n, or sometimes people just take the full group as n. Okay, so this is the orbifold construction, and one of the interesting results about conformal net is that if you start with a rational, and you take the fixed point algebra of this A tensor n, and the action of G, you also get a rational net. So if A is rational, then this A tensor n, G is also rational. Okay, so this in the setting of conformal net is a theorem, but in the setting of VOA, I think last time I checked it's true if G is solvable, but otherwise it seems to be still debatable. But anyway, so the general expectation is that if you take this orbifold construction, you will produce a series of rational conformal nets, starting with any conformal net A, right? So for instance, if you take G to be Zn, the cyclic permutation, so this would be so the wrap of this one would be a sequence of modular tensor category, right? So which depends on this n. So maybe I'll write n here. Okay. So in other words, starting with any conformal net, if you apply this construction, you'll be getting a sequence of modular tensor category n, right? So starting with A, and then we apply this orbifold construction. Okay. So from the conformal net point of view, this is a very, very simple construction, right? I should say that orbifold construction going back to physics, right? The physicists back in the 80s. Okay, so now you see on the conformal net level, taking the orbifold is a really, really natural construction, and also we have this powerful theorem which says that you always get rational conformal net out of the orbifold. So you start with this A, there is corresponding modular tensor category, and then apply the orbifold construction, you will get a sequence of modular tensor category, right? So that's what conformal net tells us. So now if you look at the reconstruction program, and suppose you believe that this problem always has a positive answer, then this would translate into the following thing. So given this C, you should be able to get a sequence of modular tensor category. Let's write Cn, right? If C comes from the representation of A. Okay, this is what at least you would expect this will happen. Okay, so that's provided you know this already, right? But if you don't, let's say if you just give an abstract modular tensor category, how do you actually produce this sequence of modular tensor category Cn as if they are the representation of the orbifold of the corresponding conformal net, right? That's hard to think about. So the reason I'm introducing this is because this motivates some results in a positive direction. So so we can see that if the reconstruction problem has a positive answer, then we must have this, right? So I think I can report a little bit of positive result in this direction. So maybe the first thing I want to talk about is my joint work with Zhengwei Liu, and so what we proved is that there is what we call the Jones-Westman subfactor associated with any unitary modular tensor category C. Okay, so and we proved some of the properties using the properties of modular tensor category. So in other words, we're not passing through the conformal net, right? If you know your C actually comes from conformal net, then Jones-Westman subfactor is associated with the corresponding conformal net. Okay, but we don't have that at our disposal because we don't know whether the reconstruction problem has a positive answer or not. But at least this, the question was motivated by the reconstruction problem. So what we prove is that, you know, starting with a modular tensor category C, we can produce something like a Gell-Mann. My to prove it for cyclic group or to examine the properties of the corresponding modular tensor category coming from the OB-fold. So that remains to be done. Okay, so there are definitely some work to be done, but yeah, but I don't think anybody has done anything along that direction. So if you wish, this is a little bit of positive result. So I hope I make myself clear. So let me recapture what I just said here. Okay, so I want to give you a little bit of positive result and along, you know, related to the reconstruction problem. We didn't solve the reconstruction problem, but assuming that the reconstruction problem has a positive answer from the very simple construction, which, you know, simple in the sense that, you know, is simple on the conformal net level or on the VOA level. It's in the OB-fold construction, the permutation OB-fold construction. But then we can translate that, you know, guided by that construction, and you know, maybe we think we're confident that this may have a positive answer. This will produce a sequence modular tensor category Cn as if the Cn comes from the representation of the corresponding OB-fold of the conformal net. Okay, so in other words, maybe I will draw the following diagram. So if you have A, you have rep A, that's C, right? A has this OB-fold construction. You can take A times N. For instance, you can take Zn, and you talk about the representation of this Cn. This would be a modular tensor category, right? This would be a Cn modular tensor category. Okay, so that's provided we have this upper side, right? We have this conformal net starting with modular tensor category. We don't have that yet. So what I'm saying is that at the lower level, from modular tensor category to this Cn, we managed to do something. So this is represented by this A and B. So these are positive results, which examine the expected property of this Cn, and we show that indeed it has the expected property, as if it comes from conformal net. Okay, so that's what I meant by the positive result. Okay, so I'm not sure if I make myself clear. So if there's any question, please let me know. Okay. All right. So yeah. So that's one. You know, as you can see, this is really a tiny bit of a positive result. The other direction. Let's see 3 and 4. So let me add a few more points to this problem. So so another thing which I think can sort of serve as, you know, something positive along, well, maybe I should say that maybe evidence for a positive answer to the reconstruction problem. So there's this what let's see who Muger and Ostrich and others, they define what's called a Witt group, right? Witt group of modular tensor category. Okay, so I think the definition is the following. So if you have C1, this is C1 equivalent to C2 if C1 tensor with C2 bar. So this is a modular tensor category. So C2 bar simply means you change the braiding from overcrossing to undercrossing. Okay, is equal to the double of some fusion category. Okay, so that's the equivalence class. And turns out, and this equivalence class, modular tensor category form a group, and Ostrich and his company has made the following conjecture, which is very, I think, very reasonable. The conjecture is that the weak groups is actually generated by modular tensor category from WZW model. Okay, so all the a compact group with a level K. Okay, basically that's what the conjecture is. Okay, so is this a positive evidence? Well, it's not a clear-cut evidence, right? If this conjecture is true, at least we know up to this equivalence, right? All the modular tensor category will come from conformal field theory. Okay, but of course this this equivalence class basically trivialize the Haar group side factor, right? So from that point of view, it's not. I mean, for some people that's a big no-no. But anyway, so at least, I mean, modular this equivalence class, you see that modular tensor category should come from some kind of conformal field theory. Okay, so it's if you wish, this could be an evidence, but it's rather weak for some people. Okay, maybe I will talk about one more. So this let's see, right. So one thing here, which is so this is a rather general question. Okay, so given modular tensor category C, I have already defined the C bar. So C bar, what is C bar? C bar is that you just, maybe I will just write the diagram here. You replace all the overcrossing by undercrossing. Okay, that's what C bar is. Okay, that's also a modular tensor category. Okay, so C bar is also a modular tensor category. Okay, so suppose that the reconstruction problem has a positive answer. So if C is isomorphic to rep of A, okay, and let me assume that the reconstruction problem has positive answer. Okay, so maybe I'll write it in this way. If it has a positive answer, then C bar has to be isomorphic to some representation of something, right? Maybe I'll write, for lack of better notation, maybe I'll write A bar here. Okay, so what is A bar? So I think that's a reasonable question. I think this is sort of just by looking at the problem, you immediately see that if you have your favorite modular tensor category from representation of A, then what is this mural, okay, or C bar? What's the corresponding conformal net or VOA whose representation would give you C bar? Well, there's a candidate. Okay, so candidate has something to do with coset. So the conjecture, so many people have expressed this. So I think one candidate is that suppose this A or VOA is actually embedded into a holomorphic one. So B is holomorphic. Okay, in other words, the representation of B is trivial. Okay, and suppose that A prime intersect with B. So this coset, and so it's verify some non-degeneracy condition. So basically it means that the double commutant is equal to itself. Okay, this commutant with B is equal to A. Okay, so some kind of non-degeneracy condition. Okay, then the rep of this A prime intersects with B, this coset is going to be isomorphic to, so let's write C bar, okay, where C is equal to rep of A. So in other words, you take your favorite modular tensor category and suppose it comes from representation of A, either a conformal net or from a rational VOA, then the claim is that that conformal net or VOA has to be embedded into a holomorphic one so that it's competent, verify this non-degeneracy condition, and also the representation of the coset gives you exactly C bar, okay? So this is a very natural candidate. And in fact, in many examples, this turned out to be the case, okay? But to prove this, in general, seems to be, a difficult problem, okay? So let me just finish with, to prove this in general, is not a simple question. Okay, I have no idea how one might do this abstractly or in general setting, but in the last 10 minutes or so, I'd like to offer at least in concrete examples, this seems to be doable. Okay, so this is what I want to do in the last few minutes. Okay, so before I do that, so maybe let me just point out that in case number 3, I use the fact that the net has very simple natural construction of orbifold, right? And that leads to a question about the corresponding modular tensor category. And there are 2 positive results along that direction. And in the last part, I'm using a feature of modular tensor category, which is a very simple one. A modular tensor category naturally comes up with this mirror image, right? So you just replace overcrossing by undercrossing, you get C bar. That's a very natural construction of modular tensor category. But on the net or on the VOA, that's not a simple construction, okay? But if you believe in the reconstruction program, that problem, or if you believe the reconstruction problem has a positive answer, that forces you to prove a result which I just stated here, right? So a candidate, the proposal is that any VOA or conformal net can be embedded in some holomorphic one so that the commutant verifies some, looks like a technical condition, but this condition is very natural. This condition, very natural condition in the theory of coset, and this representation will give you exactly C bar, okay? So hopefully you guys see, the general pattern here, right? Because, from either side, very natural construction looks not so easy from the other side. Okay, so that's my point. All right, so let me just in the last few minutes offer my thoughts on this last problem. So this, if you wish, is a very natural problem coming from the reconstruction problem. Okay, so what I can offer is that if you take A to be WZW model, so let's take A to be WZW. Okay, so we have let's say a simple group, compact loop group of some level K. For any such case, it looks like it's going to work, but modulo some technical details which I will briefly mention in the end. Okay, if you take any WZW model, so let's take G. Let's take G to be simply laced. Okay, in that case, this G is well known at the level 1. Is actually, so if you take its maximum torus, is the maximum torus level 1. So that's a lattice VOA, okay, or lattice conformal net. So this is going to be a lattice, okay, conformal lattice VOA, okay, and the lattice is an even lattice, I should say. This is even lattice, okay, and so in other words, the level 1 is embedded into a lattice, okay, but of course the level K is going to be embedded in G1 cross G1 K times, right? Because the level is additive and a tensor product, okay? So this is going to be a lattice VOA, okay? When you tensor the lattice, you still get lattice. So GK is embedded in the lattice VOA. And here's the result I learned recently from Dong. And the lattice VOA, any lattice VOA, let's say even lattice VOA, is embedded into unimodular lattice. Let's write this lattice as, maybe I'll write this B, okay? Unimodular lattice simply means that corresponding lattice VOA is holomorphic. Okay. So in other words, if you take simply laced WZW model, many people think this is a building block of the rational conformal field theory in general, then this GK is embedded into a holomorphic lattice VOA. Okay. So at least part of this is true, right? It's embedded into holomorphic one. But what about the other part? So we want to check that GK prime intersects with B. We want to show, so no problem. The problem is to show this coset is also rational. And I expect this to be true in general, but one may have to enlarge this lattice or in some sense, okay? And so you should also satisfy that technical condition mentioned earlier, that the double commutant is equal to self, okay? If you can do this, then you will succeed in showing that the building blocks of conformal field theory, the WZW model, for instance, verify this problem, verify this conjecture, which is motivated by reconstruction problem. Okay. Yeah, I think that's all I want to say. Thank you for your attention.
Thank you very much. Any question?